the other day. I'm Javier Pimas. I'm working for Systems, now Javier. And I'm going to talk about this project that started really short time ago, less than a month, which I called Dan, because Dan implemented a lot of low-level stuff in all the small talks. Maybe I realized that I might have called it Richie, because he's our expert in low level, so I don't know what the name is going to be. But the idea was that I was having a lot of problems for measuring the performance of the VM. I wanted to optimize, but when you want to optimize, then you have to ask yourself, how do you measure the speed of your VM, of your code, right? So the first thing you can do is to just take a lot of benchmarks that are known in the community, and you can check against, for example, other virtual machines, other implementations. So the first thing you do is to just run those benchmarks and compare against what others have. Okay, so if you have a worse time, you say, okay, I'm bad in this, I'm bad in this, and then you know in which benchmarks you are slow, but you don't really know why you are slow, right? So you have to start thinking about what is the code doing and how you can get an idea of what your VM is doing slow, right? The idea is that you have to find what are the bottlenecks in your code, because you could optimize anything in your code, but if that thing that you optimize is not executed frequently, then it's a waste of your time to optimize that. So it's important to get an idea of what is the slow code that is being executed frequently, right? And then you may ask, how can I measure what things are going on in the virtual machine? So the main way of doing that is by profiling, right? Profiling is basically trying to measure what the code is doing, what your application is doing. There are many kinds of profilers. There are basically, what does a profiler do? The profiler collects information, right? It's going to collect, for example, which is the code that is executed more frequently, or which functions are most used. And it's also going to collect probably code traces. That's basically the state of the stack at some point, so that then you can check what that stack represented. I'm going to look at that a bit later. So how do they get that information? There are many ways of getting that information. There are some kind of profilers that could be said that are collaborative, right? Because the way they collect information is just by generating native code or code that from time to time calls the profiler, so that the profiler can get a snapshot of the stack, and with that snapshot the profiler gets information. So you need to have a specific support for the profiler to do that. For example, there are many ways of doing this. For example, you could say, I'm going to generate code that in each invocation of a method is going to increment a counter of the amount of times that method has been invoked, right? So each time you use that method, you invoke that method, you get the counter increased by 1. And after you run your application, you can check all of your methods, how many times they have been called. That's just a way. For example, here we have some assembly code that could be used to do that, and actually we implemented that just for a test case. It was useful, but not the best approach. There are, for example, another example is to have a global counter of the amount of work you have been doing, and when you reach a threshold, you are going to just call the profiler and say, collect what is in the stack, right? It's more like, in this case, you get a snapshot of all the stack. In the previous one, you only got a count of the method that was invoked and not all the state, not who calls the method or things like that. There are also another kind of profilers which I called external, which are implemented by using support from the operating system. The idea is that the operating system is able to create processes, pause processes, make them work synchronously with other processes. So it's very, very good at reading their memory, writing their memory, scheduling, and doing some things like that. And operating systems usually provide a programming interface for stopping processes and doing a lot of things from another process. So you could, for example, run your application in one process and debug it from the other and things like that. So the idea was, I have this problem. Let's check before here. This is a native code profiler. It's called Excel. It's a tool made by AMD. And it's basically prepared for profiling code written in C++, in C, or things like that, so that when you compile it with a normal compiler, you get a lot of debug information, and the profiler is able to read that information and to get basically the information about where is the code, which address represents which function, right? But in B, what we generate is a Windows executable that doesn't have any kind of debug information, and it's very hard to create that debug information because the format hasn't been open until recently, and it's very complex. So we don't have a lot of debug information. So what we got from the profiler was just addresses of functions that were executed frequently, but we had to do a lot of work to understand which functions corresponded to which addresses. We only got the addresses, and then we had to do some kind of reverse engineering. So what could we do? We could, for example, use the operating system interface to pass our process from time to time and check the memory of the process to see what the value of the stack was. And if we knew what is the value of the stack, then we can collect information for ourselves and also look at that information, but from Smalltalk. If we use an external tool, we are not able to control that tool. It's very hard to tell the tool, these are the addresses, these addresses correspond to these functions and things like that. You cannot give much information to the tool. The tool is there and you use it or you don't use it, but you cannot modify it. So the idea was to make something similar in Smalltalk. So what do you need to do to implement that? Basically, you need to wrap some operating system functions. In this case, this is for Windows, so you have to wrap some Windows functions. For example, the create process function allows you to run an application. If you pass a special flag, you can say that you want to debug that application. So when the application generates debug events, you will get notified. There are some functions like for reading process memory or writing it, or for allocating memory in the remote process, or for waiting for the debug events. You just have to wrap that functions. You have to wrap some structures. Okay, for example, a Windows structure for collecting the debugging information, or the context of the processor when it's stopped, and things like that, right? And after you wrap that, you can just do something like this. You run the process and you wait for events, right? And if you do what is in this cycle, you are going to just run your process until it finishes, and it's going to run normally, right? This is the simplest case. For example, Windows tells you when you load the DLL, or when the process has been created, or when it's finishing. But what we wanted to do was to profile the processes. So how can you profile then? You have to insert from time to time breakpoints. You have to tell Windows that you want to break the process into the process. So you are going to do something like this. The code is not that complex. What you get here is a main loop, which is run process, and it's going to wait for events, and from time to time it's going to check basically the status of the process, and if there is an event, it's going to continue. It's not going to do much more than that. When you start, you are going to start that loop, and also you are going to start another process that from time to time collects a sample of your process, right? So the idea is this: you have your process running on one side, and you have your timer on another, and from time to time you are going to say, I want to collect a sample. So how do you collect the sample? Basically, you are going to tell Windows that you want to break the process, you want to pause it, right? And after the process is stopped, it's paused, you can collect the state of the registers, you can read the memory, you can write the memory, and you can do whatever you want with it. It's just like what you see in computer organization classes. You work with a processor in assembly, where here you can do whatever you want, the process is yours, you can do anything you want. So for example, here what we see is that when we want to collect the trace, we are going to place the stack elements into an array, and what we are doing is to get the main thread context, which is the one in which we are interested, and then we are going to collect the instruction pointer. This is EIP, which in the line that says EIP assign context EIP. So we get the actual EIP of the processor that was running when we stopped it, right? And we add it to our collection, and we also store the contents of the stack base. And with that thing, we get basically a frame in the process. And then we can loop, we can continue going down in the stack until we find the 0 and collect all the return addresses. And all that return addresses are going to tell us in which functions we were. Right? A return address to some offset into a function basically means that we made a call from that function. And so this was the main idea, and it took like a few days to implement the wrapping and the main loop, and just only 2 more days maybe to have the profiler running. And so then I'm going to show how it works and how it looks. But then I said, okay, but this is like what I did was to wrap the debugging information, the debugging API of the operating system. So the most useful thing you can do with that is to debug your process. Not only to profile it, but you can debug it. You can see the registers, you can pause it, you can insert breakpoints, you could do whatever you wanted. So then I said, okay, let's try to debug our process. So this is here, but I don't know why. The idea is that with this same API, you can debug any process that is running, any native processes, not just our Smalltalk, but any native process that is in your system. You can run it in a controlled way and debug it. Our case was to debug B, but you could use this for anything. So I think this is like the dream of any low-level programmer. So you just have access from a very high-level programming language to a process, and you can do whatever you want with it. So I'm going to show some demo of some things that we have done with that. So wait. Okay, so tenemos esto de aquel lado. So here I have whoops. Sí.
But you have always. Let me take that. But you can get all this providing information only when you, in the breakpoint of the process, you're not everywhere, not any time. Okay.
Yeah. Actually, you can see the value of the registers when you have paused the process, because if not, the process is changing all the time the values. So you have to pause it first, and then you have to check the values of the register.
Those breakpoints are in the process you are debugging. So
yes.
You are in advance. Okay.
You don't have to add the breakpoints in advance. You can tell Windows to add the breakpoints in the moment you want. So. Usually Windows will in some way do it. For example, one way to do that is Windows could, for example, insert a new thread that is calling a function that only says interrupt me. So it pauses the process, it calls this new thread, and this signals the interruption, the debug event, and then everything is handled that way. But you can also insert the breakpoints. We are going to see that. El único problema es que no veo, a ver si puedo. Voy a duplicar.
Sí. Con el de expresar.
Ahí estamos.
Sí.
Uf, no se ve nada.
Cambiar la resolución.
Acá. Ah, sí. ¿Qué será esto? 1024.
Se le pone la cosa.
Okay, so here we are seeing the same thing, both of us.
Poner el mantener porque si no.
Okay, so what I'm going to do here is to tell Dan to create a new process, to launch the process, and to profile it. So this is really not the best quality because it hasn't even been integrated. I did this in like 2 weeks, the last 2 weeks. So it's very not the best code, but there it's profiling. You can see here in the top, you see the mouse pointer? Yeah, right? There it was executing. This is the CPU usage. It was actually profiling a B process. What you see here, we are inspecting Dan, which tells us a lot of things, and at some point we have the profiler, and we can tell Dan if, I can't remember the name of the method, but we can get it from here. We, for example, could say complete stack traces. I think this one is going to work. Okay, so what we get here is basically a collection of collections in which we have the stack traces, which is basically the return addresses that we got from the running process. right? So from all the information that it collected, we are getting all the stacks that were there. So there we have addresses, right? They are not very useful. They may be useful, but they are not the best. So what we can tell Dan is to do something that, for example, CodeXL doesn't know how to do, because we can't tell CodeXL to do this, is, for example, to take the names of the methods from the exports in the DLL that is generated with our B process. So I should look for Dan again to ask him how I have to load the symbols. Here, load symbols, okay, it's easy. Yeah. It's going. Yeah. So it's going to take a while because this is not very fast. But it's going to load the symbol. That's done, and then we can again compute the stack traces. And now what we are seeing is that we have names there. Not everything is a name, because, for example, there are things that come from the operating system. The operating system called us, so we have, for example, let's see a stack trace. There we have the operating system calling itself a lot of times. No, well, actually it's backwards. So the last thing in the collection is the entry point. So we did a lot of things, and we paused the process when we were in an FFI call, right? So here we don't know what all this is, right? So we have the names of the things that are in Smalltalk, but not the names of things that are from the operating system. And we can see a lot of these things, and we can see, for example, here that there are mixed things. For example, here we are executing add, and this was called by do, but I don't know why do was called, and there are a lot of things that were not called, that don't have a name, were called but don't have a name. And these addresses are, if you have a VM developer I, you can see that there are low addresses, and they come from actually your processes. So you say, okay, this is my processes that doing something, but it's not an address of the main VM, but maybe probably from a library that was loaded from our VM. So something that we can do is to say, okay, but what if we inspect the memory of the process, and this is a Smalltalk process, we know how it should look. We could make like an interface to the memory of that process and start looking at where things are. For example, we could look in that process, where is the Smalltalk dictionary, and in that Smalltalk dictionary we can check for all classes, so we can start mapping addresses to a lot of objects that are known in our world but are not known, for example, by the standard profiler CodeXL or whatever. So what we do is to add basically a model of that, that would be B. It's a model of our executable, right? It knows how to read the memory of that executable and to get a lot of information. So what we can do is to tell Dan to talk to B and to load all the symbols that are in a backtrace. So we are going to do this. Well, this may not work today. Okay. Yeah, it doesn't matter. But what basically you can do is to tell it, load all the symbols that are in the backtrace. You can load them, and so that we can see what is the full contents of the stack, not just some addresses that are in the kernel, but all the Smalltalk. We can check all the Smalltalk, and we could see a bit of that in the B process. So we are going to check again these native tools. No, we are not going to save this. We have here is the remote Windows process, native B process, and this is where we get all the information. So basically, you have to tell in this object how to get things from the process. For example, here I'm giving a name of a class, and what this does is to check for the slot. What this method does is I'm going to give you the address of a class, and it's going to give me the name of the class. And to get that, it's going to say, okay, I'm going to look at the slot of that class that is called name. And how I'm going to get it? Well, because in my smalltalk process, in the current process, I have an object called class which has an instance variable name, and I can say, okay, give me the slot number of that instance variable. So then I can calculate the offset in the target process and get the value of that string. And that's how it works. And finally, I'm going to show another demo of what else you can do with this. So here we have the browser, and what we are going to do is to just tell it to run the process, right? Not to profile it, but to run it. So here what we have is a debugger, but this is not a classic smalltalk debugger. This is more like a native code debugger. Here we have the code stack, here we have the registers. We can see the values of these registers, and here we have to disassemble native code of that of the function that we are showing here.
This is of a different process, right?
This is of the different process, yeah. The process that I have just created. So I launch the process and I let it run. So for
the environment, you launch another smalltalk.
Yes.
And you are still inspecting all the processes.
Yeah, its memory and its registers and things like that. We can see, for example, in the transcript here that the last event was create a process, load the DLL, and an exception event. This is when Windows tells you that the process is ready to launch. We can, for example, let it run a little more. We can resume, and it's paused again. We can resume again, and we are going to see in the top here that at some moment the CPU gets used because it's going to run the process and let it run because it's not generating any event. There it's running, so I can pause it, and at any time, well, there I paused it, and what I could do is to inspect, done, tell it to load the symbols. This is not done, this is done. Okay, it's going to take a while. Okay, and now here we have the names of the methods that are being executed in the remote process, right? And we can see them now. And what we can also do is now it's going to work, I think. I'm not sure. No, it's not. It's well, okay, that's not working yet. But you can load the symbols of all the rest of the addresses, and basically you can do whatever you do with a normal debugger for native code. You can say, for example, I want to skip and go on. At some points, you can get some problems in debugging, but this is native code, and you are working with native code. So basically, that's it. So if there's time for any question.
Okay.
So, okay, you now have this debugger, and so what you're checking? Because you wanted to do some profiling.
Yeah.
Then you realize that with the same, almost the same effort, you have the debugger. Now, what's your objective? What's
Yeah.
your goal?
Actually, I forgot. I forgot. I forgot because there is also an UI for the debugger that Guillermo helped me to create, and there's also, well, I also want to thank Seba that helped me with creating the interface for the debugger. So okay, there's not much more time, but basically you can see all the most frequently executed methods in a Smalltalk interface with a chart that is very good looking, and then you can check what is the most slow code that you have and try to optimize that. Okay.
Okay, thank you very much. Now it's time for the show. Remember that those who want to stay to see the project he's working on,
Okay.
and stay. If not,